So in the previous lectures, what we talked about was we had a sort of lowbrow approach to understanding first quantized string theory. We looked at the theory on the world sheet of the string. We could sort of in some way for the free string solve it and understand some of its physics. Now we want to go back and do the whole thing, to do everything more correctly, more elegantly, in a way that will more easily generalize to interacting theories. Okay? So the structure we're going to use in this part of the course, that we're going to heavily employ in this part of the course, is a structure that we discovered in our analysis of the number go to action. And I'm going to emphasize that one thing that we already emphasized in the previous lectures, but let me emphasize it again. The thing that I'm going to emphasize is the following: that the action that we got on the world sheet of the string had a metric on the world sheet of the string, okay, and some other fields. In this case, there were 26 x mu's, some Lagrangian, which is a function of the metric, and 26 some other fields. The aspect of this action that I'm going to emphasize that is of most interest to me for the next few minutes, is something that we saw very clearly, that when we did this, when we got this structure from the number go to action proceeding classically. Thank you. Thank you. Thank you. So this is a world sheet indices. Thank you. Okay. Yeah. So the thing that we saw very clearly was that GAB, that if you took GAB to, GAB tilde was equal to GAB times e to the power 2 phi for any function phi, then we got the same action expressed as a function of GAB tilde as we got as function of GAB. Okay? So our action was, while at least classically, was while invariant. Okay? Now, when we made the quantum theory, we took great pains to retain this while invariant. Because if you remember, the way that the number go to action was equivalent to this Polyakov kind action was that every solution of the number go to action was equivalent to an equivalence class, mapped to an equivalence class of solutions of the Polyakov action, the equivalence class being generated by Weyl transformations of the metric. So we wanted to solve the same problem we wanted to solve. We had to be very careful to promote this theory to a quantum theory in a way that preserved this invariance so we could continue to mod out by it. Okay? So it was very integral to the whole structure of our analysis that we wanted to deal with theories that were while invariant on the world sheet. Yes. 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 That you cannot, and it's not needed to cancel. Yes. It's physical. Mm-hmm. Yes. So it's a. Yes. Now you're absolutely right. When we complete our job, we will have got rid of that term as well, as you will see. Let me just give you a preview of the answer. Okay, let me give you a preview of the answer. Let me say it. You see, the coefficient of that 1 by L dependence will turn out to be what is called the central charge of this conformal field here.
Okay, so you will get rid of central charge by
introducing the ghosts. Okay, so in the end, for any quantity we will actually compute, even that quantity will go away. Okay?
And there was no 1 by L square. I don't remember.
No, there was no 1 by L square. It was exact.
I remember 1 by L was there, but this will
precisely get rid of that.
And then you take this data.
Yes. So this is actually the difference between conformal and while invariant theories. You see, you can have a theory that is conformal and while covariant. Let me say again. See, if you've got two different manifolds and they're related by Weyl transformation, in general, as we will see over the next 3 or 4 lectures, in general, the partition function of this theory on these two manifolds for an arbitrary conformal field theory will not be the same.
Oh, this is exactly the C.
It's the same thing, yes.
Difference is C, and make the comment.
Yes. So in general, the partition function of these two manifolds will not be the same. They will differ by a factor, that is by a function called the Liouville function, okay, a Liouville action, that is a function of this
Liouville action
of this phi, and is controlled completely by one parameter. This parameter is the central charge. And for many purposes in physics, where conformal invariance is all that we want, this is correct and is physical. However, in this string theory, we want the partition function to be completely independent of the wild factor. So it will not be acceptable to us that it depends on this wild factor even in a relatively trivial way.
In conformal field theory this is allowed, in wild field theory this is not allowed.
This is not allowed, and we'll take great trouble to remove it. Okay, that's, but you'll have to hang on. D equals 26 from this point. Okay, great. Any other questions or comments? Okay, great. Yeah, so you will see that from this more sophisticated point of view, you will see where the 1/24 comes from. Maybe you remember, you might still be worried, okay?
24 plus 2 is 26.
That's true.
If that's what you want to cancel your C.
No, but I was trying to address the following concern that I thought you might have had. You might have thought, well, there's a contradiction in two things I told you. A, I told you that 1 by L term is a fake. It's got to go away. But B, I used it to derive something physical. Okay? I used it to derive that the dimension of space-time was 26. I used it to derive the mass of the tachyon, which was both those were correct statements. Okay? Now,
but you can get them in other ways, yes.
Yeah, we will see that 1/24 in a more sophisticated way of thinking has another origin, which is the same origin. We'll see. We'll see that it comes from the matter part of the central charge, which is cancelled by the ghost part of the central charge. So it was basically correct, but yeah.
And you'll be a factor of half in between the matter part and ghost part.
That's right. Okay. Okay. But let's get there. Okay. So all of this was meant to be motivation for the fact that what we're going to do in the next 2 or 3 lectures is to try to study more generally the structure of field theories that have this wild invariance. But as we've sort of emphasized at the beginning, there's a weaker thing we can do, that is study theories that are conformally invariant. And then later try to ask, when is a conformal field theory also wild invariant? So this is the path we're going to take. Okay? So what we're going to do now is, for the next 2 or 3 lectures, study conformal field theories, CFGs in 2 dimensions. Okay? For much of this part of the course, we will work in Euclidean space. Okay? We will come back to analytic continuation to Lorentzian space later on. But to start with, let's work in Euclidean space. And the first thing we want to do is to establish some conventions. Okay? So through this course, Z will refer to sigma 1 plus I sigma 2. So sigma 1 and sigma 2 are Cartesian coordinates in the plane. This is sigma 1, this is sigma 2, x and y. Okay? Z will be sigma 1 plus I sigma 2 without any factors square root 2, like we did in Lycone gauge. So Z bar is equal to sigma 1 minus I sigma 2. Exactly. By analytic continuation, sigma 2 will go to tau. So it's the same convention. Okay? Fine. Now, 2, 3 other things. Firstly, what is the metric in these coordinates? Well, clearly, the metric is dz bar. Just because a plus b to a minus b is a square plus b square. When you substitute dz is d sigma 1 plus I d sigma 2. Okay, so the metric is just dz bar. Next thing we're going to ask is, what is del square? Okay, so let's, so the line element was dz bar, which meant that the metric was gz z bar was equal to gz bar z was equal to half. Okay, so now this means when you invert, a matrix which has 1, 1, 0, 0 is its own inverse. So if you've got half, half, 0, 0, then the inverse will be okay. So let's figure out what del squared is. So del squared is equal to gz z bar del z bar plus the other term. Okay, so that is equal to 4 del z bar. Okay, and the last thing that we will define is a volume element, d2z. Okay, this d2z we will define to be what you would get by taking absolute values of Jacobians. Just forget the, so look at the coordinate change between z and sigma 1, sigma 2. Forget there's an I, okay, or maybe even take an I, it doesn't matter very much, and do the coordinate transformation. Okay, so anyway, I'm going to define it as d sigma 1, d sigma 2, with a 2 d sigma 1, d sigma 2. This is what you would get if you just plugged in the determinant formula. Do you know what I mean? Del z by del sigma 1, del z by del sigma 2, del z bar by del sigma 1, del z bar by del sigma 2. You get 1 I minus I 1. Compute the determinant, you get 2. Okay? Fine. So these are the conventions that Polchinski uses, and we will try to, and one or two more things. Del z is equal to del 1 minus a plus, oh, I del 2 minus 1. And del z bar, I'll check the, oh, del 1, let me check which way. No, I think it's actually, because it's down, I think it's okay. Yeah, one way to check this is to check whether del by del z on z bar, acted on z bar, you get 0. Okay, and because z bar has a plus, that will kill the minus. Okay, okay, so conventions all clear. Great. Now, there are many interesting ideas in quantum field theory that are very nicely illustrated in this two-dimensional context, and will be of great use to us as we proceed in our study of quantum field theory, proceed in our study of string theory. And I'm going to start this, I'm going to now introduce some of these ideas. Okay. The first idea, this is an idea that's actually specific to conformal field theory, is this thing called the state operator map. Okay. So whenever you've got a conformal field theory, you've got this fantastic thing called the state operator map. Okay. Now, in order to understand this, I first want you to note a trivial kinematical fact. Okay? The trivial kinematical fact that I want you to note is this, is that the cylinder is while equivalent, to the plane. Okay? In order to see this, let's do the following. Let's say that on the cylinder, so say I've got a cylinder with the real coordinate going along the space direction, and the imaginary coordinate going along the, so sigma 1 going along the space direction and sigma 2 going along the axis. Okay? And I do the following. I define W to be equal to sigma plus I times tau. Okay? Now, suppose I make the conformal coordinate change, the kind of coordinate change that can be undone by a wild term. at least locally. Okay? I make the conformal coordinate change, z is equal to e to the power I. You remember that in Lorentzian space, as we talked about in the last class, x plus being any function of x plus and x minus was any function of x minus gave us conformal diffeomorphisms. Those, what? Do I want minus w? Oh, what do I want? Okay. Maybe I'll put a, you want me to put a minus here, and then what I should do? Something stupid here. Maybe I'll put a minus here. I want e to the power I sigma. Okay. I want time minus infinity to, yeah. Let me do this, if you don't. Then there may be a more standard choice. This will work. Okay, and then z is equal to e to the power minus iw. Maybe I should look up Kolchinsky's choice. Z is equal to e to the power minus, oh. Yeah, sorry. So he does it without this. So he has a sigma going the other way. So I'll just stick to his choice. You say that z goes like e to the power minus I. That's okay. Okay. So W is sigma plus I tau, and z is equal to e to the power minus I tau. Okay. I want to first convince you that this coordinate change takes this cylinder to the plane. You see, exactly. Yeah. Okay. He doesn't. He finds this more ugly than that. Okay. Fine. So look. What is this coordinate change doing? Firstly, the norm of z, the absolute value of z, is completely set by the part of this thing that is not phase. So let's write this out. So this is e to the power minus I sigma plus tau. Okay, so it's equal to e to the power tau times e to the power minus I sigma. So the absolute value of z is e to the power tau. So where you see constant time slices here map to circles on the plane. Right? The angle on the circle is simply the angle on the cylinder up to this minus sign. Angle measured one way is angle measured the other way. Is this clear? And as time increases, the size of the circle increases. As time decreases, the size of the circle decreases. Okay? So do you see that this change of coordinates gives you a conformal diffeomorphism? I mean, gives you maps the cylinder to the plane, and does so by using the coordinate change that is of the sort that can be compensated, whose effect on the metric is of the sort that can be compensated by a Weyl transform, and therefore conformal transform. Yeah. Now you see, it's true. In my strict definition of a conformal transformation, I was mapping one space to the same space. So it's not a conformal transformation that way. But locally it is. Now, you might think that, see, t equals minus infinity is the place that would map to the origin. Okay? And strictly speaking, I should remove the origin. But nothing goes wrong if I keep it.
So you do some contour integral or something, can you take the contour?
As long as, you see, as long as nothing is nothing, you see, the way you would see that the origin was a strange place if you just did this coordinate transformation. Let's do it. Okay? So suppose we took that the metric here on this space was dw bar. Okay? And we want to explore what the metric is on this plane. Now let's solve for w. So we see that w is equal to I log z. So dw is equal to I by z dz. So what you see here is that this is minus dz bar divided by z bar. The fact that the z bar factor is blowing up near the origin. What? The minus won't be there probably. Yes, you're right. 1 I and minus sign. Thank you. Thank you. It should be positive difference. Yes. Thank you. So dz bar by z bar. The fact that this thing was blowing up was what was telling you that the origin was a strange place. Okay? However, you see, we're not going to work with the space with this metric. We're going to then do a Weyl transformation that removes this factor. So once we've done that Weyl transformation, the only price we paid is that we are allowing ourselves to do an infinite, a Weyl transformation that diverges. But once we've done that Weyl transformation, there's nothing funny about that. So we can just complete the space. And that's how we take a space that takes, that sort of changes topology. Right? Adding these points, because after I've done this, the metric is completely smooth. That allows me to do it. Is this clear?
Yeah. So the Weyl transformation takes you from C union infinity to this C.
If you allow yourselves to add that point in, and there's no reason not to in the new metric. It's natural completion of the new metric. Okay? However, this point will come back to us. You see, the question of what happened at the origin is a question on the cylinder at what happened at t equals minus infinity. Now, t will be time for us. And what happened at t equals minus infinity will be a question of the initial state in our. And if the initial state is not nothing, then that will map to this z plane with an operator insertion. So in some sense, that point is removed. It's a special point. Okay? But it means, the operator could be identity, in which case it's okay, but all excellent questions. So let's keep going.
When I consider equation on a plane, what metric do I consider? Is it bar or the factor in
Well, I do the Weyl transformation to get rid of this. So I'm trying to relate the physics of physics on the plane with the standard metric. Okay? To the physics of physics on a cylinder with the standard metric. Okay? If I were to relate the physics of physics on the cylinder to this metric, to physics on the plane with this, I've not done anything. This is just a coordinate change. This you could do for any quantum field. The thing in a theory that has good transformation properties under Weyl transformation is that it allows you to get rid of this. And now you've done something very interesting. You've taken physics with a standard flat metric on the cylinder to the flat metric on the plane. Okay? And this is not possible for any quantum field theory. It's only possible for quantum field theories that have good transformation properties under Weyl transformation, in particular for conformal theory. Okay? Great. Now, the reason I did this was the following. Once you have the cylinder here, suppose you analytically continue this tau to time. Then we've got genuinely a Lorentzian cylinder. This is the problem we looked at in previous classes. We had a theory where space was a circle and time was time. This is a standard kind of problem we look at in quantum mechanics. Okay? This is the problem if you're dealing with a good field theory, has a good Hilbert space. Is this clear? So once we go here and we do an analytic continuation, we've got a usual Hilbert space, and it's a good theory. It's got a unitary inner product. And all of that. Okay? Now, I want to make the following claim. Okay? I want to make the following claim. I want to make the following claim. The claim that I want to make is the following. That in a conformal field theory, okay, there is a map between states on this cylinder, states on the cylinder, Lorentzian, good states on the cylinder, and local operators of the theory, which we will insert on R2, but the map will be between states on the cylinder and local operators, period, because local operators are local operators, no matter where you insert them. Okay? This is the claim of the state operator map. Okay? I'm going to try to explain this claim to you. And we will understand this claim better as we understand in more detail how conformal transformations act on operators. But first I'm just going to tell you the structure of the claim, and we will come back to it as we understand the theory better. Okay. So, where does this claim come from? Firstly, before even starting to understand this claim, I want you to understand how surprising this claim is. In a quantum mechanical system, states are vectors in Hilbert space, and operators are matrices. And if you've got an n-dimensional vector space, you've got an n-square dimensional matrix space. There's certainly no one-to-one map between states and operators. Okay? That's just not true. If we were saying that there was a one-to-one map between states and operators, this would just be a wrong statement. But we're saying something a little more subtle. We're saying there's a one-to-one map between states and local operators in the theory. Okay? So let me try to establish this claim. At first, roughly, and as I said, we will understand it better and better as we go along. And in establishing the claim, you will also understand what I mean by a local operator. Okay? So, I want to, okay. So, in order to establish the claim, I have to show you that given an operator in the theory, I can uniquely produce a state. And given a state in the theory, I can uniquely produce a local operator. So given a local operator in the theory, I can uniquely produce a state. And given a state, I can uniquely produce a local operator. Okay? So I'm going to prove both statements for you. First, let's do the easy one. Okay? Given an operator, let me produce a state.
Also unique.
What? Also unique, yes. I'll give you a procedure to do it, so it'll be unique. Okay? You see, this cylinder was used to motivate the Hilbert space. But now let's try to write this Hilbert space entirely in language on the plane. So now, in order to do that, I want to introduce an idea that all of you know in some language, but to put that in front of your head. And the question I'm going to ask you is, what from the point of view of path integrals is a state in the Hilbert space of the theory? Okay, so let's go back and review things all of you know. When you read Feynman and Hibbs or wherever you learned about path integrals from. Okay? Yes?
We should remember that we do quantum mechanics with time domain independent of time as well.
Yes, you can.
So let's not assume that your D is something that depends only on the, and this is not a conserved quantity. I am asking this because I really want to understand that what are the assumptions that go.
But at the moment we're talking about a conformal field theory. So it will be a conserved quantity.
It will be, but this is why I am
yeah.
making the comment that I want you to say what goes wrong in quantum field theory.
Yeah. I'm going to stick at the moment to conformal field theories. And we could have an exercise in that. Why don't you, I'll set you an exercise to compute this in a massive scalar field, massive free theory. That will make it all very clear. Okay? So we'll have an exercise where we do some of these constructions explicitly in the massless case, and also explicitly when we turn on a mass. Okay? I think that will make it very clear. Okay, great. Just in a free theory, which will illustrate many of these ideas. Okay, but at the moment, let's focus on the conformal field theory. Okay, so the first thing I want to do is to just remind you how you think of a state in language of path integrals. Okay, so in language of path integrals, suppose I had an initial state in just quantum mechanics, Feynman Gibbs. And I wanted to compute the final state. Okay? What did you do? I'll remind you. What you did is this. You computed the path integral dx e to the power plus is, where s is a function of x of t, and this path integral runs over all fields x of t between time t1 and t2, between initial and final time. But now we're going to ask the question, what about the initial and final times? You path integral, you break up the times into discrete things. You path integral over all time, integrate over all times intermediate. But what about the initial and final time? If you want precisely this question, what you're supposed to do is to do this for some given x at the initial times, let's call it x initial, and then integrate that x initial over a measure given by the initial wave function. So the Feynman-Hibbs path integral is a path integral fixing initial and final time. If you want the question of how do you take an initial state to evolve to a final state, you do that path integral with fixed initial and final time. Then you take the initial time and integrate it over the wave function, the initial wave function. Now, once you've done this, the final answer is some chi, which is a function only of x, final. Okay? And that, I may be getting the stars. I need a star in one of them. I'm putting my star in the initial. I don't even need a star. Sorry. Yeah. That final answer is interpreted as the wave function you get by starting with the initial state and evolving to the final time. Okay? This all of you know in some language. Because the Feynman path integral is the transition amplitude between x initial and x final. And then all I've done is to take e to the power I minus I h on psi initial. And then I've inserted the complete set of states here. So I've got e to the power minus I h on x psi initial integral dx. Okay, and then I've also introduced a complete set of states here. Y, and then I've taken this with psi final. Yeah, so I did need a psi star, right? No, I didn't. I'm sorry. This is y. No, I didn't need the psi star. It's y, and whatever comes as a coefficient of y is the final wave function. Now the coefficient of y here was the path integral from x to y multiplied by the initial wave function and integrated over the position of the initial wave function, which is what we've written here.
You start with a state, you end up with a state.
With a state.
You don't reverse.
You don't reverse.
You
That's
don't
right.
get-
That's right. Yeah, because you end up with a ket. Exactly.
You can do this with Hamiltonian time dependence.
You can do this with Hamiltonian time dependence.
Yeah,
Absolutely.
I have some comments, so I just want to.
Please make your comments. Okay. Fine. So what is the point I wanted to make? The point I wanted to make was this. Suppose you've got a path integral which is a local operation in time. You may be doing the path integral from some initial time, you may be doing it from t equals infinity. You could be putting some operator insertions here. That would change what you're doing here. But if you're interested in the final state, what you're supposed to do is do whatever path integral you're interested in, but freeze that path integral at a particular position in time, the time at which you're interested in the final state. And the answer to that path integral as a function of that final position is the wave function that is created by your path integral. Okay? This is often said in the study of quantum field theory as in the following words. In path integrals you get a state by cutting a path integral. And that word is used because you imagine the path integral running from minus infinity to infinity, and then you cut it here. Stop the path integral, demand that the position is some particular y, and determine the path integral as a function of that y. That gives you a state. So cutting a path integral at a constant time defines a state And more generally, if you cut the space of all possible path integrals, define the Hilbert space of the theory. Is this clear? Okay, so this is the connection between Hilbert spaces and path integrals. You get the Hilbert space by, or states, by cutting path integrals at constant time. Okay, this is something you know, I'm just reminding you of. Now, what we wanted was the Hilbert space on the cylinder. Okay, so what we want to do is to cut the path integral at some constant time here. But we've mapped this cylinder to the plane. And we've already seen that constant time slices on the cylinder map to constant radius slices on the plane. And therefore, in order to get a state, what we have to do is a path integral on the plane, cut on a circle, and do the path integral in every over the inside. Okay? So now the first part of the map is really easy. In order to get a state from an operator, what do? I take my path integral on the plane, insert a local operator, and then do the path integral up to unit 10. Let's say the fields of my path integral are x mu of sigma. This path integral will be a function, I'll be explicit, sigma 1 and sigma 2. These are sigma 1 and sigma 2 on the plane. Okay? This path integral will now be a function of x mu of sigma. And whatever function you get is the state, the Schrodinger wave function of your state. Recall that in a quantum field theory, the Schrodinger wave function is a functional. It's a number associated with any field configuration on a constant time slice. A complex number associated with any field configuration on a constant time slice. And this that's precisely what such a path integral produces. It's a complex number depending on this function.
Is the state there a vacuum state?
Not necessarily.
For example, the lower line which you have drawn,
This one?
the equation is different. Yeah,
Yes.
this one.
Yes.
So the operator should be the first step, right? You should start from some state, then you insert an operator, and then there is insertion of all the line.
Yes.
So I'm saying, what is the first state?
That depends on what you know, see, okay, we're going to ask that in the next step, when we make a map from states to operators.
Because to do this, you did insert the psi in and integrated over there.
I did, but I didn't need to have. You know, I could have done this path integral to minus infinity and put some operators here.
Yeah.
Any path integral, when cut, gives you a state.
But I'm saying there is an initial state that has to be defined, right? You have to integrate over initial time slice with some state.
Yes, but I'm telling you exactly what path integral I'm doing. I'm doing the path integral with some operator insertion here. At the level of defining my path integral, I defined it for you.
How do you know that two operators, different operator insertions will not give you the same state?
How do I know that different operator insertions will not get? That is the next step. See, I've shown you that given an operator, I can find a unique state. That you don't disagree with. Now, next step I have to show you, given a state, I'll find a unique operator.
So this one you can do any this is a definition you can do any theory.
This is a definition you can do in any theory, and it's a very trivial thing. Because essentially what you're doing is taking an operator and acting on a predefined state. For instance, a vacuum, and that'll produce a state. Of course, operators can easily produce states. The other ones are less trivial. How do you get from state to an operator? Okay? Great.
But there has to be some convention, right? I mean, if I'm, let's say I take all the operators and I have to do the same thing. I have to start with the same state for all the operators.
What is the state? I've got a Euclidean path integral and I've got an operator insertion.
Yeah, this origin is
The origin is a perfectly smooth spot.
put in, and that seems problematic if I'm thinking in terms of cylinder pitch.
No, but I'm not thinking in terms of cylinder pitch. I'm not claiming that there is, this operation requires me to be working on the plane. Okay? Some of what you want will be answered by the second step. But you have to but it's important to understand that what I've said is completely okay on its own terms. Why has the plane been essential? Well, not really. You could.
I mean, this is just a general statement about path integrals.
This is a statement about path integrals. In the next step, everything will be very much more essential. And this part was a trivial part. Okay. Now let's move to the next step. Now what I want to do is, given a state, I want to define an operator. I want to define a local operator. Now, what do I know about this local operator? I don't know very much about it. But I do know that when I insert it into the path integral, according to this step, it should reproduce the state I started with. It should be the state dual to the operator, according to my prescription. So I want to produce something like this. Okay. So in order to do that, I do the following construction. I've got my plane, and now I remove the unit disk. Because I know my state, I know psi of x mu of sigma. That's what it means to know state. Okay? So any path integral to the exterior of this unit disk is now well defined. Okay? I'm going to define it like I did here, where I rubbed it out. Suppose I'm interested in some path integral with some number of operator insertions. So I'll show you this path integral. Suppose I'm interested in and with some operator insertions. Let's say O1 at sigma, let's give these a name, x mu1, x1, O2 at x2, and so on, all in the exterior of the disk. I want to do a path integral over the exterior of the disk. Okay? This path integral I'm going to define by the following. I will do the path integral over exterior but such a path integral is only well defined if you specify what x mu is at the boundary of the disk. That's the nature of path integrals, right? You do a path integral from one time slice to another, you have to specify x at the two time slices. So this is specified as x mu when I know what x mu of sigma is. And then I take the state psi of x mu of sigma, and I also path integrate over psi of x mu of sigma. So this is d psi, the dx mu. Dx mu, this is exterior of unit disk. And then e to the power minus s and all the operator insertions, O1, O2. The whole exterior. Now, well, I'm just getting a number.
I'm sorry, you are getting something that you are doing it all
Overall, all of space.
You are getting some.
Just a number.
Yeah, that's okay. Yes.
Yeah, I'm just getting some number. Okay? I want to emphasize that unless you had a state on the boundary of the disk, you could not get a number. Because a path integral in a space with a boundary is only well defined once you tell me what your fields are doing on the boundary. So you get an infinite number of different numbers. But now I have a distinguished way of choosing out one of the numbers by taking this psi of x mu and integrating also over x mu on the boundary of the disk. Yeah? Okay. Tell me which part. Was this operator to state part clear? Okay. Now what I want to do is this. Given a state, which is a function psi of x mu, I'll imagine the state is defined on the unit disk. I want to define a local operator. Okay? This is part one of that procedure. The first part is, given a state, I want to uniquely define a path integral with any number of insertions on the exterior of the unit disk. So you put operators at any points on the exterior of the unit disk, and I want to give you a number associated with that. This is my goal. Is it clear? So the way I'm going to do it is this. First, I just do the path integral with the operator insertions to the exterior of the disk. That, however, is not good enough. Because that path integral, to be well defined, needs me to tell it what x mu was on the boundary of the disk. So I do it with some specified x mu, and then path integrate over x mu of the boundary of the disk with a weight factor given by the initial state. This now gives me a number. Is this clear? Now, this is sort of interesting already. Why is it interesting? Because you see, suppose I were to define an operator for you. What is it? A local operator is some local modification of the path integral that allows you to associate with the path integral and any other insertions a number. Let me say that again. Suppose you have some operators that you know about, you know and love. And I'm going to define a new operator that you've never heard of. Okay? Your operators were O1 to OM. And I'm going to define a new operator, let's call it B. Okay? In order to do that, what I need to do is to tell you the rules for arbitrary numbers of insertions of B and all other O's inside the path integral. When I insert some operators and I do the path integral, I get a number. So what I need to do is to give you a rule for how to compute the number when I insert this operator. What? Yeah, absolutely. Absolutely. This you can do in any theory. It's only the last step which we'll use. Okay. Now, the way, so, you know, if I were to define my new operator, it would be this. If I tell you the rule, so if I insert my operator at the origin, and you put your operators anywhere else, that is anywhere but the origin, if I give you a well-defined rule for how to compute the answer, okay, I've defined the local operator. Okay? This rule, moreover, at least in path integral formulation, is a rule that should not change what you're doing to the path integral outside a neighborhood of the origin. So it's not just a rule, it's a local rule. But of course, that's associated with the fact that you are allowed to put these other operators anywhere on the plane. Okay? Now, I've gone halfway there in my construction. Because given a state, I've given you a rule for inserting operators to the exterior of the unit disk. This is almost there, but not quite. Why is it not there? Why is it not quite? It's not quite because I've only allowed you to put operators to the exterior of the unit disk. If you ask me, what is the answer to putting operator insertions to the interior of the unit disk? I have no way of answering that, because my rule only works when insertions outside. Moreover, it's clear that I've not defined a local deformation of the path integral, because I've drastically modified the path integral over the whole interior of the unit disk, and a local operator insertion is modifying the path integral only in the neighborhood of one point. Okay? So, pretty good, but not good enough. Now, how do we do better? How we do better is the following. Look, let's first freeze these operator points to be to the exterior of the unit disk. Now I'm going to ask, can I change my path integral so I do a path integral over more of space? Instead of working on the unit disks, suppose I want to work on the disk of radius half. Okay? Can I find a rule that will tell me how to do that? But the answer to that is very simple. The answer to that is very simple because, you see, I gave, all we need to do is to see what state, when inserted on a disk of radius half, would give the same path integral as the given state on the disk of radius 1. However, from going from radius half to radius 1 is achieved in the cylinder picture by translations in time. So this is given by the action of the Hamiltonian in the cylinder picture. Okay? So all I have to do in the cylinder picture is to take my state and translate it in time. Okay? Translate it backwards in time. Okay? By some amount, and then I will get the state I need to insert for the path integral on the radius half disk. That state is guaranteed to give the same. So now there's a second problem that I will solve to get the same number. The second problem is use the new state on a path integral on a disk where we path integrate everywhere to the exterior of a disk of radius half. Path integrate also for the field values on the disk of the radius half weighted with the time translated state. Okay? And the fact that the path integral between half and 1 generates time translations, generates evolution under e to the power minus beta h, and the fact that I've gone from the initial, the first state that I weighted on the disk of radius 1 to the next state that I used to weight on the disk of radius half, these two facts together guarantee that I will get the same answer.
I give you a state on the unit circle, you time when the time in the backward direction, and those slightly inside and get another state.
I get another state, and now I do a path integral with this state on this disk, and by the definitions of the path integral, this is going to give you the same answer.
Nicely. So this you do at a big scale.
It can include other
What?
points.
What?
This can include other points.
Exactly. Now that I've got this, for all insertions to the exterior of the unit disk, it gives me the same answer. But now there is a natural way of extending this. Yes, to have operator insertions to the exterior of the radius half disk. Okay? But if you can do radius half, you can do radius quarter. If you do radius quarter, you can do radius 1/8. And so you can shrink to 0.
But this, all you are doing is given a state on the unit that you are going to till 30 for the unit circle, and you are time going in the opposite direction in time. You can do that in other theories.
You can do it in other theories. However, in a theory where the Hamiltonian is symmetry of the theory, it's guaranteed to be good action. It's just like,
I totally agree that if your scaling is set, if your scaling is dependent on R is the radius of a circle, then this is not a good operation. But in principle, you can do this operation.
you can do this operation. You might, at the expense of potentially getting very singular things. Okay? But in the case where time translations was a symmetry of your theory, these were time translations on the cylinder, but scale transformations on the plane. Both are symmetries of the theory. Scale transformations independently we knew was a symmetry of the theory because it's conformal field theory. Scaling is a
So you will say that the existence of the limit
is the problematic thing.
is the statement that this is my symmetry of operation, so use it.
Exactly. Here we're guaranteed that everything will be good.
If everything boils down to existence of a limit.
Exactly. So let's focus on the limit that Indrani is talking about. First I shrunk, then I shrunk, and I kept going until my circle was at an infinitesimal size. But now look at what path integral I'm doing. I'm doing a path integral where I'm modifying the path integral only in the neighborhood of a point. But that is the definition of a local operator insertion. A local operator insertion is a local modification of the path integral. You don't change the path integral anywhere except that in the neighborhood of a particular point, and produce well-defined rules for computing all insertions. But this is what I've done. So by doing this shrinking, I've taken this huge hole eaten out of the path integral and reduced it to an infinitesimal, to a region smaller than anything you could care to imagine in particular. And therefore, I've defined a local operator field.
So, one of the key things in this picture is mapping the whole T equals 0
Exactly.
Which makes it local.
Exactly. Exactly. That's totally key.
That's why the plane is useful, right?
That's totally correct. What? Am I assuming unitarity? I don't even think I'm assuming. I mean,
When I give you on the unit here and then you want to go back, it will give information. I just want to know, you know.
yeah. Well, certainly it'll work if. Yeah. So what would go wrong? Maybe I'm assuming unitarity. Let's think about that. What I'm assuming is that time evolution by a conserved operator can be carried on for an infinite amount of time. Okay, and because it's conserved, that's sort of clear. Right? It doesn't change things. Give me an example of the non-unitary theory you have in mind, and maybe. Yeah, but give me an example of. Okay, let me. I will hesitate to make a general statement. In a particular certainly what I'm saying will work for a unitary theory. I suspect it will work for many non-unitary theories. But there might be some, for instance, if in Liouville theory, I know it doesn't quite work. Okay, that's an example of a non-unitary theory.
So the
where
diagrams are knowing this
you know, the things that are subtle are things like this. If I give you an operator insertion here and I get a state, I get a number as a function of x mu of sigma. But to be a state, that number as a function of x mu of sigma has to be more than just some number of function of x. It has to be normalizable, for instance. Okay? Now, in this picture, when everything is working well, we know that that is correct. Because, you know, you can go back to the cylinder and do something at very early times, but then all you're doing is translating by a conserved charge. Okay? If in that process something weird happens, let's say that you had a Hamiltonian that depended on time like e to the power minus t. You know, something that started really blowing up as t went to infinity. Then that could, in the limit t goes to minus infinity, perhaps produce for you a non-normalizable state. You know, that's the kind of thing that could happen. But in our context, because all we're doing is translating by a conserved charge, nothing terrible could happen. You know, state remains a state. All that changes phase.
Although you haven't defined inner product here, but you soon define that, okay?
That's right. That's right. That's right. We will come back to this more cleanly as we.
You have just given them an example that it does not work in at least one of the non-unitary theories.
Yes.
Therefore, the unitary is assumed.
Yeah. So yeah. However, I think that in the non-unitary minimal, minimal models, it will work. I think it will work. I think that you might be able to get away without unitarity with some other assumptions. Okay, but certainly unitarity will be good enough. Okay, I don't think unitarity is strictly necessary.
So as we gone to epsilon level and we have subtracted that region only,
Yes.
saying that equivalent to putting some operators on that point, right?
Yes.
That's how the equivalence.
Yes, that's exactly how the equivalence works. Okay? In particular theories, actually we will study non-unitary theories in this course. You know, the BC system is non-unitary. State operator correspondence will work fine. Huh? Yeah. So there'll be many non-unitary theories in which it'll work okay. In specific theories, we will examine the state operator map in detail to see how the guts of it work. That's when you will really start getting comfortable with the map.
But then you will also say for BCDCFT, just to extend the comment, why do you want such states to be lines or something because they are in your ghosts? I don't know, I'm just trying to.
Why do you want them to be nice?
Suppose I give you a non-unitary theory. Which state will you perform? To say that in this theory, state operator are false. For BCCFT, it will come as a ghost, right?
So see, I mean, in the kinds of CFTs that which check will I perform to say that the state operator works in a non-unitary theory? Well, I should be able to make, as long as the theory is such that the Hilbert space of the theory is well defined, even if it has negative norm. You know, in a state where,
Sorry, I know I am asking.
yeah, can we move on?
Yes.
I mean,
Yes.
yeah. Okay, yeah. Okay. So, yeah. So, so let us summarize. Okay. What we have done is to establish a two-way map. Firstly, a map between operator insertions and states. And secondly, and much more non-trivially, a map between states and operator insertions. Okay? Moreover, you see, a state on the cylinder transforms in a particular way under time translations. Okay? And in Lorentzian time, it transforms like e to the power minus IET. But if you do the Wick rotation, the I will go away. So it will transform like e to the power E times t. But e to the power E times t was simply the radial coordinate of the z plane, if you remember. Okay? So what I'm saying is that the state in question transformed under shifts of time like e to the power delta t times E, where E was the energy of the state. Okay? But e to the power delta t was a scaling of radius, the ratio of the two radii, initial to final. Okay? So what we've just deduced is that the operators, that the transformation of the operators under scale transformations where you blow up all of space, is related to the transformations to how the states in question transform under time translations. Okay? And the precise version of the statement will be, and we will see this as we go on, is that the scaling dimensions of the operators in question under the state operator map. We'll define scaling dimension and so on, but you have an intuitive feel for this. Well, the scaling dimension of the operators in question will map to the energies of the states under the state operator. Okay? So it's a very precise map. More of the spins of the operators will map to the angular momentum of the states. That just comes from the fact that that translation in sigma on the cylinder, which is angular momentum, was rotation on the plane. Okay? So there is within the space of conformal field theories, at least good conformal field theories, I don't know what the criterion for goodness is, and certainly unitary conformal field theories. Okay? But within the space of conformal field theories, okay, there is a one-to-one map between states of the theory on the cylinder and local operators of the theory, and the map is a very precise one. The scaling dimensions of operators map to the energies on the cylinder, spins of the operators map to angular momentum on the cylinder, and so on. This is a remarkable fact which gives us great control over the spectrum of local operator insertions in a conformal field theory. The kind of control that is sort of, that would otherwise be hard to get. Okay? And as an example of this, okay, firstly, any questions or comments about this? Yes. Yes. Only at the origin. That's great, except that what we're doing is we're defining a local operator. So once I know the rule for how to deform the path integral about the origin, I can apply the same rule at the translated point. You see, so the rule will be, for instance, like change the path integral around the origin in some prescribed way. But then I can translate that rule. So I'll change the path integral around sigma in that same prescribed way. Since it's a local quantum field theory, there's nothing special about the origin. Is this clear? What state will be that again? Well, you see, it depends on how you cut the path integral. Suppose I take my operator here, okay, and I translate it to this point. Now you have two options. You could cut the path integral like this, in which case you'd get the same state. But the more interesting question is, what state will we get if I continue to cut the path integral like this? Okay? Now this will be some complicated state. It will be sum over this operator and various descendants because of translations. We'll understand some of this as we go. Okay? If this state will be re-expressible as a linear combination of states with all operators at the origin. So it's a very good question. We should think about that a little more. The question was, look, I put in the first part of my procedure, I defined a map by putting an operator at the origin of space and doing the path integral. But had I put an operator anywhere inside the unit disk and done the path integral, I would still have got a state. Of course I would. However, the map between operator insertions and states on this is nice and canonical if I insert here. So, but since I must get some state here, and we've established that there's a map between states and operators, inserting here must be the same as inserting something else there. Now in this game it's actually quite simple. We know what, because it's a bunch of translations. Yeah, so in this case it's very easy, because we just have to translate, and translation is given by derivatives. So it's very easy to figure out what state you would have to insert at the origin. Do you know what I mean? I mean, all I'm saying is that if you want to insert, if you have phi of alpha, you want to write that in terms of insertions at phi at 0, use Taylor expansion. Okay, so this is equal to sum over n del mu alpha mu, yeah, you know what I mean, right? Yeah. Del mu 1 del mu n alpha mu 1 alpha mu n phi by n factorial. Taylor expanded. And these are now insertions at this thing. So just translation is a very trivial operation, but we're going to do something less trivial just now. Okay, but it's a good question along the lines of what we're doing. Yes?
The first way, when you split an operator, do the path integral and get a state on this.
Yes.
What is the time slicing that you can consider here?
Maybe I didn't understand your question.
Yeah. Then I have the same question actually again. That what is the time? What is the state that you're starting with, on which you're? Can I take any state I want, or
I'm doing a path integral.
Yeah. So path integral has a t equals to initial slice and t equals to final slice. Here t equals to initial slice.
Here there was no t equals initial slice. I'm just doing a path integral.
You're not cutting with an initial state. I'm telling you what path integral to do. This is path integral. It's not, you are not cutting with a state. You're cutting with a path integral.
You see, you would have had an initial state and a final state if your path integral had two cuts.
Yeah.
Our path integral has only one cut, so there's only one state. Okay? The number of times you cut the path integral along this is the number of states that you're looking at. Yes? How do you get the uniqueness of the local operator? Well, you see, given the state, I translated it backwards using the Hamiltonian on the cylinder, or equivalently the dilatation operator on the plane. Okay? Now, this is a unitary operation. So I just work with that unitary operation. So it's unique. Okay? Okay. As I say, we will understand this better when we look at examples. Okay?
My question is, you go to the
Yes.
you say that is equivalent to a local operator inserted there.
Yes.
Is it equivalent to only one unique operator there?
It's equivalent to a unique operator because, let's take the circle to be size epsilon. I knew what psi was at 1, psi of x mu. So I get a particular psi epsilon of x mu, and that completely defines the path integral. Okay? Now as I take epsilon to be smaller and smaller and smaller, this gives a particular modification of the path integral around that one. Therefore it's unique. Uniqueness is the same as knowing what to do to the path integral at that point, and what you do is modify it by psi mu of x. Since this psi is entirely well defined and unique. Okay. Yes.
Originally we said that we started with summation.
Yes.
We said that different operators in that region would be sort of expressible, like in terms of linear combination with the one at the origin.
Yes.
So is the argument that as we shrink this down smaller and smaller, any operators in this region will sort of become the operator at the origin plus some like corrections with their magnitude?
As we move this operator nearer and nearer? Yes. So if we move this operator nearer and nearer, it's just this Taylor expansion. Let me write the Taylor expansion out more legibly. See, given a classical field, phi of x mu, if I want to expand this classical field around the origin, what do? I take x mu, mu1, x mu n, del mu1 to del mu n by n factorial, acting on phi, and then evaluate all these derivatives at 0. Okay? So that's the kind of thing that's going to happen here. We'll talk about descendants of operators, but they're essentially derivatives. Okay? And as you see, as x goes to 0, only the leading term, n equals 0 contributes, as you said. Okay? Other questions or comments? Yes, go on, go on. Why is it specific to conformal field theories? It's because this operation, see, the first part was not specific at all. I mean, going from the operator to the state is completely generic. However, going from this state to an operator involves doing an infinite dilatation. Okay? And when you have something going to infinity, you're in the danger of producing something not well defined. Okay? The fact that you were translating by a conserved charge, at least in a unitary theory, okay, guaranteed that that would be okay. You're just evolving for an infinite amount of time. That's not a bad thing to do. Okay? However, if you were in a more general theory, that limiting procedure could run into trouble. You could be formally defining something, but it would be some very singular object. Okay? The fact that this whole dilatation procedure is governed by a conserved charge is sort of what's clear. Okay? Excellent. Additional questions or comments? As I said, I'll formulate a question on this, in which you do it for massive and massless scalars, and you will see the difference.
So, given one state, one can presumably find a number of operators inserted at different points, which makes it a non-local operator, and presumably there might be a huge number of them, right?
You're saying there are many different operator insertion ways of getting the same state.
Yeah.
Sure.
And
Sure.
only one
Local operator. Yeah, exactly. Exactly. For instance, in fact, what we're going to do next will illustrate this. Okay. So, the next question we're going to do, the next thing we're going to do is to take what we said, what we just discussed completely seriously, along the lines of the questions. Tell me your name again, please. I know, I've taught you before, I should know, but anyway. Sunil and, yeah, okay. So, great. So along the lines of the questions that that have just come up, we're going to take these questions very seriously and run with them. So we're going to do something a little more non-trivial than you suggested, Sunil, but along the lines of what you suggested, which is we're going to put one operator here and another operator here. Okay? So it doesn't actually matter very much. Suppose I've got two operator insertions. So I've got two operator insertions in my path integral. Okay, and I've got an infinite number of, I mean not infinite, but a large number of other operators. O, H1, H2. However, my operator insertions have the property that I am able to encircle operators O1 and O2 by a disk that do not also encircle any other operator insertion. So suppose I'm interested in calculating a correlation function of this. Yes?
In this Euclidean picture, the distance is really like a positive definite quantity.
Yes.
So given two operators, we will ask this question.
Yes.
It's a Lorentzian case.
Right.
What will be the corresponding statement? When this probability is valid?
Yeah, I think everything that would be valid would come from the Euclidean theory and analytic continuation. So,
If I give you a Lorentzian configuration,
yeah,
in the first step, to the Euclidean picture and see.
exactly. So in Euclidean picture, you will have a certain radius of convergence of a particular OP, and then you can take that OP and make it complex.
Suppose there is no other operator, two operators are there.
Right.
Now, put them any match, say a conformal field theory.
Yes.
OB is convergent in Euclidean.
Yes. Yes.
Now, if you analytically continue with taking one of the directions sign,
Yes.
I'm just trying to understand this formula.
Yes.
Take any one direction of sign,
Yes.
make the Lorentzian.
Yes.
Then, if you are convergent all over the space, like
Yes.
there is nothing.
Yes.
Then are you saying that it will converge? Oh, then you are saying that everywhere, then inside or outside the number, everywhere it is converging.
Well, it's converging, but you know, you have to be a bit careful because in Euclidean space, all of Euclidean space corresponds to space-like separation in Lorentzian space. Okay, so when you go past light cones, you're doing something that you never that essentially is like O1 going to O2.
This is the statement I would like to understand. If you are two dimensions, you have two coordinates. If you make one of the Lorentzian,
Yes.
then you can draw a light cone like this.
Exactly. So suppose we look at the distance in Euclidean space. The distance is, let's say, one of them is at the origin, the other one is at z. The distance is mod z square. Now z will continue to x plus, sigma plus, z bar will continue to sigma minus. So we'll go to sigma plus, sigma minus. Okay. In Euclidean space, this thing was always positive.
Now it can go to 0 when you go to the null cone.
It goes to 0 when you go to the null cone, and that clearly is governed by the singularity of what happens when the two operators come together. And then it can go through in Lorentzian space, which it could never have done in Euclidean space.
So is it the outside of the, so it's, are you saying the OP is valid when the space like separated?
Well, the OP is valid when they're space-like separated, and then anything that follows by analytic continuation from there. When the time-like separated, again, there must be some region where OP is valid. But that will come from this analytic continuation. Right. Maybe it's only valid. You see, let's say better. You see, once you go through time-like separations, even the notion of, you have to give orderings.
You have to clear orderings now.
Yeah.
So just
So it's a, yeah, there are many options when you go through time-like separations.
many ways of analytically continuing.
Many ways of analytically continuing, and it's a complicated
Then
picture.
you have to somehow distinguish one of the ways to say in
To
this
say
way,
that, to even talk about it, right?
in this way the OP is valid.
That's right, that's right, that's right, that's right. Okay. However, we're not going to worry about Lorentzian OPs at the moment. But please go on, yes.
Then I will,
No, no, please go on. Yep, go on, just go on.
if you are calculating correlation function,
Mhm.
in hat one state and hat one state. If you have two states,
Mhm.
which are called hat one.
Mhm.
If this is the usual correlator, now you can put two different states.
In Minkowski space, you're saying?
Yes, in your conformal field theory,
Mhm.
doing this correlation function between two had one state the same as doing as two different states, because you can trade
Yes.
the correlation function in the state phi 1 and phi 2.
Yes.
Same as doing the two operators and then we'll do it in head 1. But
Yeah.
this statement will not go through
In Lorentzian space.
This is another statement I am asking.
Yeah, yeah.
First the OP statement and the second one is this statement.
Right. So firstly, what you are asking is that if I wanted a cylinder picture from state to state. If I wanted to compute some state at initial time, operator insertions on the cylinder, and some state at final time. That will map to the plane with this state being mapped to the operator inserted here, the other state mapped to the operator at infinity, and these states, these operators mapped wherever they are. That is absolutely correct. Now, what was the question again?
Now, in Lorentzian signature,
Lorentzian signature where? If you were Lorentzian signature here? Okay, good. So Lorentzian signature, suppose I wanted to compute state, that would be the analytic continuation of this quantity, because that quantity is the analytic continuation of the Euclidean path integral that computes it.
okay.
Yeah.
And one more. Yeah, but but the first question was about OPE.
Yes.
Unity of OPE.
Yeah, but maybe I should.
This one is for the state operator now. Okay.
But maybe I should say what the OPE is before the.
Oh, sorry.
Yeah, before the questions come. Yeah. Okay. So see. So suppose you have two operators O1 and O2, and you've got this disk. Okay. Now I assume only that there exists a disk that surrounds these 2 points and none of the others. Now I can play my game again. I can break up the path integral in this region to the path integral here, the path integral on the disk, and the path integral outside. The path integral here, as a function of the field values on the disk, produces a state on the disk. And then you can use that state to do the path integral outside. The whole path integral creates the state. Okay, but we've already seen that given a state, we can replace it by a local operator at the center of the disk. Moreover, that operation is local, by which I mean it concerns only the path integral to the interior of the disk, and so is entirely insensitive to what insertions there were outside the disk. What is this? So this is the statement that suppose I've got O1 at sigma 1 and an insertion of O2 at sigma 2. Okay? Now, for simplicity of notation, though it matters not at all, I'm going to put O2 at the center of the disk. Though everything I say would work, as long as you could surround these 2 points by a disk, neither of them needs to be at the center. Okay? O1 at sigma 1, O2 at sigma at 0 is some sum over OM at 0. Because it's some operator. Yes, these operators are all operators, not necessarily primaries. Because it's some operator. Now why did I write this as sum over operators? I wrote it as sum over operators because of state operator map. The state operator map told us it's a one-to-one correspondence between operators and states. And in states, we have this lovely theorem that in a Hilbert space, any state in the Hilbert space can be expanded in terms of its basis. Let's use an energy eigenbasis for the Hilbert space. So any state in the Hilbert space can be expanded in a convergent expansion in terms of the basis of that Hilbert space. Associated with each basis vector, there's a corresponding local operator. Let's call those OMs. So I've got some operator through this procedure. That operator, whatever it is, can be expanded in a linear sum over the OMs. Of course, what these linear sum coefficients will be will depend on sigma. Okay? There will be some sigma dependencies here. We will see exactly how we can figure out the sigma dependence. What the coefficients will be, it will depend on sigma. But this fact is true and true on very general grounds. What have we used here? A, we've used that we can do the path integral get a state. B, we've used that every state can be expanded in terms of a basis because we've got a Hilbert space. And C, we've used the state operator map. Given the basis states, they map to basis operators. What I want you to really emphasize is this, that this algebra here is entirely local. It's not that it's true once I tell you what the external insertions are. It is true entirely independent of what the external insertions are. And therefore is a statement about the operators themselves and not about particular correlation functions. About statements about particular correlation functions would be basically a triviality. Okay, finding some relations between different functions, you can always do that. What makes this entirely non-trivial is that it's true for arbitrarily many correlation functions, whatever insertions you put outside. Okay, this thing here is called the operator product expansion. The fact that the product of two operators inside a path integral can be expanded in a basis of in a sum over local operators. Okay, and that this is true in a conformal field theory follows more or less straightforwardly from the state operator map. It also gives you the criterion for validity, that you can enclose the two operators inside a circle which includes none of the other operators, because then you can use the path integral to produce a state. Is this clear?
And what are the number of states in the Hilbert space will be the number of operators in.
Of course, Hilbert spaces usually have infinite number of states, so there will be an infinite number of operators. But more interestingly, the number of states graded by energy will be the number of operators graded by energy. And when you grade states by energy, that gives you finite numbers. You can actually count. What? These ONs are not necessarily primaries. And expanded in terms of all operators. Okay? Primaries will have their own role, which we see. There can be a different operator. That's the case when you have degeneracies in the Hilbert space. That's fine. Whatever can happen when you expand states in basis of Hilbert space basis can happen for these operators. But it's fine, we're very used to dealing with all these issues.
So the fact that there's a correspondence between operators and states, does it constrain the operators in some way, because as you were alluding to earlier, operators we can consider as n square and states as n.
Yeah, but the key point is that we're dealing with local operators. Yeah. So there's this, the cut down in number of local operators versus operators is the same as the cut down from n to n square. They're both infinity, so it's hard to compare them. But the fact that it's working tells you that that's the case.
So the operator product expansion, if I understand correctly, is true not only for 2D CFDs but also for general quantum field theory.
Yes.
So is there any general governing principle that allows this kind of expansion?
Yeah, it's much harder. Okay, firstly, of course, every quantum field. So firstly, let's say various things. Firstly, every proof, all the proofs I've given, all the arguments I've given for the operator, maybe it's too strong to say proofs, all the arguments I've given for the operator product expansion and for state operator map, though I gave it in the context of two-dimensional conformal field theories, actually used basically nothing about the two-dimensional nature of the problem. Okay. It continues to be true that S d minus 1 times time is while equivalent to Rd. Proof. Write Rd in polar coordinates. Removed by while. and then write r is equal to e to the power t, exactly like we did. Okay. So this up to the while transformation becomes dt square plus d. Okay, so we've just seen that Rd is while equivalent to Sd minus 1 times time in every dimension. Okay, this radial quantization, taking the theory and quantizing it on surfaces of constant Sd minus 1, is basically working in the Hilbert space in the cylinder. Okay, state operator map goes through, OPE goes through, it works in every dimension. Okay, so as long as we are in conformal field theories, everything I've said is just generally true. Okay, in a more general quantum field theory, of course, quantum field theories by their nature are defined so that in the deep UV they become conformal. So, conformal or free. That's called free, a special case of conformal. Why in the deep UV? What is a quantum field theory? A quantum field theory is a theory that is defined by flows away from fixed points of the renormalization group. Maybe there's 20 years from now somebody will have a better way of thinking of quantum systems, and then this will be a passé definition. But as far as we understand this now, this is the way we define quantum. Which means that in the deep UV, it's at a conformal. The caveat to the statement is that this fixed point could be free. There are some free theories that are not traditionally thought of as conformal. So that's why I keep saying free or conformal. Okay? You see, if you take a lattice field theory, that is not in the deep UV defined by conformal field theory, but that's not what we call a quantum field theory. But what I mean by quantum field theory is a field theory that is well defined, non-trivial at all scales. A continuum theory. These things are by their nature defined as flows away from UV fixed points. That's the only way we know how to define quantum field. Perhaps more vaguely, when you do integrals to very high energies, you run in the risk of getting all kinds of weird stuff. Okay? And the conformal invariance tames the high energy behavior. But anyway, that's the only way we know about how to define quantum field theory. So all quantum field theories at short distances become essentially conformal, or free, but same thing. Okay? And so everything we've said applies to insertions that are short enough distances in a more general quantum field theory. At longer distances, I don't know of any proofs. Working out the OP, even whether the OP continues to be a convergent rather than, let's say, an asymptotic expansion, and so on, I'm not even sure. I don't know of more general. For instance, if you look at Weinberg's discussion on the OP in volume 2 of his book on quantum field theory, it's such a mess. And you compare it to what I told you about. Read that discussion, such a mess. Try it. What is known, what is guessed, what you see from particular Feynman diagrams, all mixed up. No. I don't think there's very clear understanding of the formal structure of OPs beyond. Surely it applies in some sense. It's used in QCD. It applies in some sense, but the precise nature of it, I don't think is very well understood outside conformal. And may even be a case where may change from theory to theory. Okay. Other questions or comments? What is the nature of the coefficient functions of the OP? Okay, I'll tell you. We're going to discuss all this, but I'll give you a quick preview. The nature of these coefficient functions, the dependence on position, can largely be deduced by scaling. Okay? So suppose I have O1 at x1, and O1 is an operator of dimension delta. What that means I have to tell you. But roughly speaking, it means that every insertion of O1 behaves under scaling, but with weight delta. Okay, I have to explain precisely, but roughly you know. And you have O2 at 0. So suppose this is weight delta 1 and this is weight delta 2. The rule is that in the OP you can match, you have to equate deltas on both sides. Okay, giving weight -1 to all positions, because positions transform under scaling, you know, with mass dimension -1. Okay, so now suppose you produce an operator O3. Let's take the special case where all these things are scalars. O3 with some dimension delta, also at 0. Then, since this had delta 1 and this had delta 2, okay, but this had delta, there's only one thing here, so there's x1, it's really x1 2, but okay, that's x1 to the mod to the power delta 1 plus delta 2 minus delta. Okay, we'll see more sophisticated versions of these formulas once we include spin and so on. But roughly it's like that. Okay, times a number, of course. So there's part of the OP that you can deduce by general symmetry principles. The number you cannot. That's a dynamic information. Okay, and that's sometimes really important information. Clear?
This is not quite similar when Taylor expansion.
This is not a Taylor expansion. This is not a Taylor expansion. It's for instance, you know, when you take, let's take a free theory. So you take phi of x of what we'll call x of x. Okay, and let's take del phi of x and del phi of 0. This thing will behave like 1 by z square, by x square, in 2 dimensions. We'll see this. There's a short distance singularity. The fact is there are short distance singularities in quantum field theories. Tell you what we're doing is far from Taylor expansion. Because Taylor expansion is never short distance. This is quantum rather than classical. Okay? The reason that the earlier thing was Taylor expansion because there was nothing for it to hit. It was just one operator. When you have 2 operators, there's a relative distance, interesting things can happen.
In that case, if you have a operator, away from 0, and if you want to expand in terms of 0, then we should not have any operator
At somewhere else or at the origin. Yes, exactly. Okay, fine. So, any more questions or comments? Shall we move on? We need to stop soon. But any more questions or comments about this? Okay, excellent. As I said, we'll get to understand the state operator map and the OP better and better as we go along. Now let's move on. Okay. There are a few more general things I want to discuss. Before turning to specific theories of interest. Okay? And one of these general things is the special interplay that often happens between Noether's theorem and conformal invariance and the analytic structure in 2 dimensions. So let me remind you of that. Let me explain that to you. Okay? To start with, I'm going to remind you of Noether's theorem and give you a quick path integral derivation of this theorem. Okay. So what is Noether's theorem? Suppose I have an action, let's say dx e to the power minus s of x. Let's say d phi e to the power phi. And the action has an infinitesimal symmetry. So phi is equal to phi prime plus delta phi prime, which is some function of phi's, plus epsilon times delta phi prime, is the symmetry of this action. When do we say this is a symmetry? We say this is a symmetry when you take this change of variables, you plug it into the path integral, and when after that plugging in you find that this is the same as d phi prime e to the power minus s of phi prime. If this happens, this infinitesimal change of variables is called a symmetry. Okay? It's of course highly non-trivial. If phi, for instance, was del phi, the whole thing squared, and you said phi was equal to psi squared, then the action which was quadratic would become quartic in psi. And so so I want to distinguish two things. Sorry, I may not have said it very clearly. Changes of variables never change the results of integrals. If you've got an integral, you want a number out of the integral, you can do that integral in any variable. The number will never change. But generally speaking, changes of variables change the form of the integral. You're doing an integral that looks different in two different variables. The symmetry is, what's important with the symmetry is that in the new variables you're doing the same integration with the same integrand in terms of the new variables as you were with the old variables. When that happens, you say you have a symmetry. Okay? So, of course, all of you can think of examples. For instance, in a theory of a complex scalar field, if you phase the scalar field in terms of the new phased scalar field, you have the same action. Everyone with me on this? Everyone understand what you mean by symmetry? Now there is this lovely theorem that you've all learnt about classically and perhaps in quantum field theory courses that says that whenever you have an infinitesimal symmetry, you have one of these infinitesimal symmetries, you always have an associated conserved current. Okay? And I want to give you a quick path integral proof of this. And this proof will sort of is a good way to think. So what you want to do is this. You know that if epsilon was a constant, by definition this did not change the path integral. Now you make the change of variables phi is equal to phi prime plus epsilon of x times delta phi of x. Okay? So what I did not say is that we expect this rule to be local. That this phi prime here should only depend on phi prime at the same point or in the neighborhood. Okay? So now what we do is to take this transformation and make this epsilon, whatever it was, just make it some function. When it was a symmetry, this did not change the form of the path integral of the integrand. Now what happens? Well, we'll get d phi prime times e to the power minus s of phi prime plus, now it can change, but all changes have to be of the form that they come with the del mu of epsilon times something. I don't even know what this is, but whatever it is. Well, if the measure does not remain invariant, I'm assuming that the path integral measure remains invariant under the thing with constant epsilon. Or more precisely, if it does not remain invariant, the non-invariance of that should cancel the non-invariance of this. So I'm assuming that this is true, including measure factors, when epsilon is constant. That's all I'm assuming. Now when epsilon is varying, either the measure or the action or both could change. But whatever the changes, okay, it should vanish when epsilon vanishes, is constant. And so must be proportional to del mu of epsilon. Now some of you may be thinking, why del mu, why not 2 del mu's? Well, if there are 2 del mu's, you integrate by parts. Put the other del mu on the j mu. Okay. The point is that because it should vanish when it's constant, there has to be at least 1 del mu. That's all we care about. Okay? Some of you may be wondering, why did the change happen up here and not down? And because epsilon is infinitesimal, up and down is all the same. You know, the change is order epsilon, and then I can put it up. Okay? Great. Now, so this is the form of the path integral. Now, let me assume that this epsilon was chosen so that it was non-zero only in a certain region. So this is my space, there's a certain region here, and epsilon is non-zero only in this region. And I have some operator insertions, O1, On, O2, On here, outside that region. Since this change of variables was local, outside where epsilon was 0, there's no change of variables we're doing. So the operator insertions have not changed. Because what is an operator insertion? It's like some function of the phi's, right? For instance, you could insert the operator del phi square. Now, if you do your change of variables, you must also do the change of variables inside the operator insertions. But if they're outside where you've defined where this variable change has occurred, it's not changed anything. Okay, so we will continue to have O1 up to On with no change. So this is equal to this. Now as numbers, these two things were always equal because it was just you're changing variables to do an integral. So this integral is equal to this integral. To first order and epsilon. So now let's take the statement and expand it to first order and epsilon. Okay, so I expanded to first order and epsilon. What do I get? Well, the term that had no epsilons in it was just the old guy in new variables. Because everything here is O of phi prime, because phi prime is the same as phi. Where they answered. Okay? So the term where I have no epsilon, where I expand this e to the power minus, you know what I'm doing, right? I'm doing e to the power minus s plus epsilon is equal to e to the power minus s into 1 plus epsilon. The term with the 1 is just the original guy, which tells us in new variables. But in integration, dummy variables don't change the number. So it tells us that the term proportional to epsilon must vanish. So what have we concluded? We've concluded that integral del mu epsilon j mu over the region of insertion times O1 to On expectation value. This expectation value I'll use as notation for e to the power minus s path integrated over everything. This must be equal to 0. But because epsilon vanishes at the boundary of my region, I can integrate this by parts without getting a surface term. So I get del mu of this is equal to 0. Okay? This is true for every epsilon in that region. The region has just been chosen so that there's no overlap with any other operator insertion. And so the only way this can be true for every epsilon is if d mu j mu O1 to On all themselves vanish, provided where j is inserted does not overlap with where either any of the insertions of the operators. This is the simplest version of Noether's theorem. That the spectrum of operators of the theory includes a conserved current. Why is it conserved? It's conserved because del mu j mu with every other operator insertion, non-coincident operator insertion, vanishes, which appears to tell you that the operator del mu j mu is 0. Now we can do a bit better. Suppose our epsilon was not chosen to vanish where the other operator insertions were placed. Then the manipulation still goes through, except that these operators are not now invariant. Meaning, the insertions as functions of phi, when re-expressed in terms of phi prime, become the insertions as function of phi prime plus some epsilon correction. Let me call the correction to the nth operator, On of phi is equal On of phi prime plus epsilon times delta n of, let's call it epsilon times delta n. Delta n is an operator. Delta On maybe. As a function of phi prime. Let's suppose this is true. You understand? This is just notation for however the operator transforms under the change of variable. Then how is this equation changed? Now when we equate the terms with epsilons, okay? Now when we equate the linear terms in epsilons, we still have one term which is del mu j mu O1 to On. But we also have sum over I is equal to 1 to n, O1, let's call it m, O m minus 1, nothing's changed here, but then OM is replaced by delta OM. And then ON. Yes, this is where epsilon, right. Let's say that epsilon now has been chosen to be something that, what? Yes, exactly. Has support. We do this for arbitrary epsilon. Let's say epsilon is anything that just dies off at infinity, so that we can integrate by parts freely. Then what I did was equate the coefficient. I got some epsilon times something is equal to 0. It's true for every epsilon. Therefore, the thing it multiplies must vanish.
Also, there will be terms where the integration by parts del mu gives the O in that case.
Where the integration by parts, no, the integration by parts is only happening on del epsilon j mu.
Yeah.
See, these are inserted at different positions. Oh, I see what you're saying.
Yeah.
There will be terms where
when they have common support, then it will also give the O's, right? The del mu.
no, no, this is an integration variable. That was the x's of the field theory. Yeah, it's how, okay, good. It's true, it will, but I don't care. I will just take it to the boundary of that region and drop the boundary term. Yeah, so you're wondering about,
No, I mean, when we transfer the derivative from the epsilon to the other part, when
yes,
epsilon and O have a common support, there will be terms, in the previous case there was no issue with that, but now there will be terms where epsilon and the del mu O's do not vanish simultaneously.
what is del mu O's?
No, I mean, when you transfer the derivative from the epsilon.
Yeah, so let's just look at all the terms. Okay, so there's an epsilon mu del mu j, which is a function of x, and O1 to On, and then there are other terms with the other epsilons.
Are these O1s and local operators?
These are O1s to Ons, x1.
Yeah, no, this will generate some contact terms, I believe.
So the contact terms are these additional pieces. Okay, see. Yeah, you know, I could.
The x is a variable between epsilon and j only.
You know, this I can do the integration by parts at this stage. At this stage of I get plus del mu epsilon j mu plus whatever. In this term here, I could just do the integration by parts. This integral,
What is the problem with integrating by parts? Epsilon, the derivative is just x. J, then it will just act at point x.
yeah.
You have already taken care of the changes, otherwise these contact terms are already written explicitly.
Yeah, I think he's worried that in this expression, it looks like there may be singularities when this x hits this O. It's the position of this. And he's worried about whether the integration by parts is valid through that singularity. Okay? And it looks like an issue if you write it that way. But let me just do the integration by parts here. At this stage of the manipulation itself, I'll make this del mu j mu. It makes it clear there's no connection between what's happening there and there. Yes. So then we just have the epsilon outside here and this del mu j mu. Okay? So in the end we get this equation here. Why, okay, let's redo that derivation. Okay. So what do we have? We have d phi e to the power minus s of phi. And this thing, when I do the change of variables, this becomes plus integral epsilon del mu epsilon j mu. As long as this is just a statement about what happens to this term locally.
Oh, okay,
It's just a change of variable statement.
that is on the exponential.
This is in the exponential. It's got nothing to do with what else is there. Okay? As a number, this is just a number. As a number, this is the same thing as this. It's a minus sign, which I'm not putting. Okay? And then I bring it down. Okay. Yeah. I bring it down, and this thing just goes through. Yeah, right. I don't think there's an issue. Okay. And then we've got these. So now this statement is what? This is the statement that del mu j mu, okay, yeah, we need to go, but it's 2 minutes. Del mu j mu vanishes within correlators unless the j is inserted at the same point as some other insertion. Now, this you might think is very weird, because I told you 5 to 10 minutes ago that whenever there is a symmetry, we have an operator, there is a current which has an operator is conserved. Now something's conserved as an operator, it's conserved as an operator, del mu j mu is 0. So how can it matter whether something's inserted at the same point or not? Okay, does anyone know?
There is an order in this.
Exactly. What is the resolution to this question? It's this. The resolution to this question is that path integrals generate time-ordered operators. Okay? Path integrals generate time-ordered operator insertions. So when you rewrite this expression, some expression like O1 to OM, in terms of what it means in terms of operators, you have to rewrite this expression involving bunches of theta functions. It's O1, O2, O3 if O's are time ordered in that order, the times of O's, or O2, O1, O3 if O's are ordered in the other order, and so on. Okay? So now this expression, which looks innocuous, is actually time ordered insertion of these O's, because that's what path integrals generate. Okay? Now what does this del mu j mu mean? What does it mean? It means insert del mu inside, it means the following. It means compute the correlation function of j mu at x plus delta x. Subtract from it the correlation function of j mu at at x, and take the coefficient of x mu. Okay? Because that's what we're doing, right? We put the definition of the derivative inside the path integral, j mu plus j mu, and each of those is an. So what this means is really this quantity, where this is acting on this, because that's what path integrals give you. Now, this quantity is full of theta functions when expressed in terms of real operators. And these d mu's can act on the operators, or they can act on the theta functions. Okay? When they act on the theta functions, they only act on the theta functions when this is the time derivative. The space derivatives don't hit the theta function in a time slicing. Okay? But when they act on the theta functions, because of this thing, what you will see if you think through this is you'll just get a J0, because time contracts with J0, and you'll get a commutator between J0 and the operator in question. And commutator between J0, since J0 is the current that generates the transformation, the commutator between J0 and that operator will produce this delta. So not only are these contact terms consistent with del mu j mu actually being 0, it's needed for that. When you actually do this del mu j mu on the time order expression, that is what came out of the path integral, you obtain this. Okay, I'll take 2 minutes more. I'm sorry I'm going so far over time. There's one point I wanted to make. Okay, everything I said here was true for arbitrary field theories. Now I want to help you understand what's sort of special about these conformal field theories, and in particular in 2 dimensions. Okay. So one of the things that we conclude is that, of course, since del mu j mu is equal to 0, j dot n integrated over space, n is the normal vector to your spatial slice, is a constant. The usual thing, that's the charge. Now what I want to do is to try to understand what j dot n works out to when we do this holomorphic, radial, when we evaluate charges on these circle slices. Whenever we give Hilbert space interpretations, when you think of conserved charges and so on, we'll always do it on these circle slices. We're always really working on the cylinder. Okay, so we're back to the plane. We're doing radial quantizations. We're working on the cylinder. So I want to evaluate j dot n on this slice. Okay. So how do I do that? Well, okay, I'll leave this as an exercise for you. Can you please check that j dot n is proportional to jz dz minus jz bar dz bar? Exactly. Take the normal to that. Yeah. Exactly. Exactly. Okay. Exactly. Exactly. Please check this. It's, as Indranil said, it's a 2-minute exercise. Okay. So what we see is that the conserved quantities. Okay. What we see is that the conserved quantities in a 2-dimensional theory, separate into a part involving just jz and a part involving just jz bar. Moreover, the current conservation equation del mu j mu becomes the equation dz bar jz plus dz jz bar is equal to 0, as you can see by using the fact that the metric upper has only zz bar non-zero. Okay. So now, so far, okay. However, something very interesting often happens when we're dealing with conformity. And the thing that often happens is that we often deal with currents. You see, if you look at this equation, it can be solved because this cancels this. But there's another way in which it could also be solved. It could be solved because jz is an analytic function and jz bar is an anti-analytic. In that special case, certainly this will be true. And it will turn out that in many cases of interest, this is what happens. Okay? So we'll have conserved currents where both these terms will separately vanish. Jz will be analytic, jz bar will be anti-analytic. In that case, this charge really splits into this plus this, where this is a completely analytic function and this is a completely anti-analytic function. In many cases of interest, in fact, jz bar will actually be 0. You'll only have jz. So the whole charge will be only the integral over an analytic function, okay, a Cauchy integral over an analytic function over the unit disk, and that will give us enormous power, as we will see in the next class. Okay, sorry for keeping you guys over time. Questions, comments, otherwise? Let's go.